Okay, continuing on talking about the reactions of carboxylic acids. This is a review reaction, how we can convert carboxylic acids into the formation into ketones using two equivalents of a Grignard or an organolithium reagent. So we talked about this in an earlier lecture, but just to go back, the idea here is that if we take a carboxylic acid and we react it with two equivalents of a Grignard, let's go ahead and put real groups in here. So let's make this a CH3, and let's go ahead and react it with two equivalents of something like ethyl Grignard. You could also use the equivalent organolithium compound as well. But the critical part is we need two equivalents of this reaction. So when we do this reaction and all Grignards are followed by a then H plus H2O step, we're going to end up adding, replacing the OH with, in this case, an ethyl group. So we're going to make that ketone. And just to not go back and review the entire mechanism, because you could do that in one of the earlier videos, but just to remind you that in this case, the first Grignard is going to go ahead and deprotonate the carboxylic acid. That's what we learned when we talked about Grignards. So it'll go ahead and deprotonate that, and then it will be the second equivalent of the ethyl Grignard that will go ahead and add to the carbonyl. So that what we end up doing is we end up then forming an O minus, another O minus, and we've added our ethyl group. And at that point, the reaction's over. We're just waiting to put in H plus and H2O, and when we do that, we're going to go ahead and protonate both oxygens to make that molecule, which is, remember, called the hydrate. And the hydrate in the presence, so we're going to use excess acid and water. In the presence of the acid and water, hydrates are unstable, and they will go ahead and convert back to the ketone, and then we would have water. So it's the reverse mechanism of forming the hydrate out of the ketone. So we talked about that reaction earlier, and so that's a way to convert carboxylic acids into ketones. Now, do you have to throw away two equivalents, or do you have to throw away one equivalent of Grignard? No, another way to do this reaction would be to simply say, okay, I'm going to take my carboxylic acid and I'm going to react it with something like lithium hydroxide first. And that's going to make the carboxylate, and then I would go ahead and add, maybe in this case, so that I don't mix metals, I would react it with the ethyl lithium. So we could go ahead and not have to use two full equivalents of the Grignard or organolithium if we just simply deprotonate the carboxylic acid to begin with. Okay, so we've looked at that reaction before. Now let's talk about reactions of carboxylic acid chlorides. And in this case, we'll go and we'll talk about how we can form different carboxylic acid derivatives out of this, anhydrides, esters, or amides. So if we take my carboxylic acid chloride here, how did we make that? Remember, we made that by reacting a carboxylic acid with SOCl2 or PCl3 or PCl5. That's how we made that acid chloride. But once we have that acid chloride, we can react it with a number of either neutral molecules or anions. So let me just show you as an example. Let's say we reacted this with a carboxylate, because this is a relatively straightforward short step mechanism. So if we react the acid chloride with a carboxylate, where did the carboxylate come from? It came from another carboxylic acid reacted with something like hydroxide or maybe bicarbonate. So we deprotonate it to form the carboxylate salt. The carboxylate then is going to go ahead and come in, add to the carbonyl. The pair of electrons will go up here. That will form an O- with a Cl with the O with that group added. Again, whenever we do one of these reactions and we form an O-, the O- would love to bring the pair of electrons back down and reform a more stable carbonyl. The problem is that something's got to leave. Well, in this case, what is a better leaving group? Remember, leaving group ability is based on basicity inversely. So therefore, if I have something like chloride versus carboxylate, which one is a weaker base? Let's say you don't remember that. Okay, fine. Let's look at their conjugate acids. Here are the conjugate acids. The weaker base is going to come from the stronger acid. So what's stronger acid? HCl. A strong acid that completely dissociates in water, or acetic acid, which only partially dissociates in water. If you go back and remember your general chemistry and your ice charts and all of that, you used a lot of that. So in this case, Cl- is the better leaving group. So that means chloride's going to leave. So I'm going to lose my Cl-. I'm going to reform my carbonyl. And I now just made a carboxylic acid anhydride. Okay. And we used acetic anhydride, where there are methyl groups on both sides, in the first step of the benzocaine synthesis. So this is how one way you can make a carboxylic acid anhydride. Now the other compounds that we make, like esters and amides, it's not going to be convenient to make the anions. So what I'd like to do is to take my carboxylic acid chloride and I would simply react it with an alcohol. That's a 100% reaction to form the ester, and I would end up forming HCl out of that. Now, what would be the mechanism for this reaction? Okay, let's go ahead and do this, and then the same reaction for the amide. Now, the alcohol is going to attack the carbonyl. You might say, but wait, doesn't it need acid? Well, the problem is that, and we'll see this in a future slide here, that acid chlorides are not stable to water or acids. The other thing is this. Carboxylic acid chloride is very reactive, meaning it's very unstable. Why? Well, in a carbonyl, we've got a delta plus and a delta minus charge. What's that chloride doing? The chloride is pulling electron density out of an already delta plus, making it more delta plus and more susceptible to a neutral nucleophile like alcohol adding. So we don't need acid for this. The alcohol is simply going to come in, and in my mechanism here, I'm going to form the O minus, the Cl, and again, I always add the entire nucleophile. Make my oxonium ion. I'm going to go ahead and then lose H+. And that's going to form this. Now, for those of you saying, wait, this is kind of a Zwitter-ion. And so if it's a Zwitter-ion, wouldn't the O minus pick up the H+? Sure. I mean, you could do that. We could simply say, okay, that O minus is going to pick up the H+. We saw this when we were adding the nitrogen compounds to our carbonyl, when we were forming imines, shift bases, and the first step of the enamines. So you could very easily say, okay, no problem. Either way you look at it, we're going to end up with an OH. Great. Okay, so now what happens? And there's no extra H plus in here. So what happens now? This pair of electrons comes down here. We lose the chloride, so I'm going to lose net HCl. Reform the carbonyl. And then all of these R's, I call them R primes because they could be different. So I'm going to form the ester that way. So we haven't really done a mechanism of reacting an acid chloride with a neutral species. And so that's how we would do it. We'll see that acid chlorides are the most reactive of the carboxylic acid derivatives. And so that's going to form that anhydride. Okay, so that's how we form an ester from the acid chloride. We saw that in the last lecture. That was a 100% reaction, and in some ways a better way to make an ester than Fischer esterification. For amides, what would I do? I basically would do the exact same reaction. So let me get a new slide here. Then go back and pick it up. So if we reacted an acid chloride with an amine, and this amine could be primary or secondary, what we end up doing is this is again a much better method to form the amide. And again, I would lose HCl in this process. Now, in the textbook, they add something to this molecule in order to make the reaction go. And actually, I should go back here and say that for this reaction to go with the alcohol, that I've left out a reagent that the textbook uses and that should probably be used. And that is that once you form HCl, one of the things that you could think about is, well, that HCl could protonate the ester and reverse the reaction. It's not likely to happen, but it could. So typically what we want to do is we want to tie this HCl up with a base. And so in this reaction, what we end up doing is we end up adding pyridine. And we've talked about pyridine a couple of times in terms of it being aromatic and in terms of it being basic. So what happens is that when you form the HCl ends up reacting with the pyridine so that nitrogen has lone pairs that are not part of the aromatic system, so that what you end up doing is you end up then forming you end up protonating the nitrogen so that it has a positive charge. And then the chloride is the counterion for that. So you end up forming a pyridinium ion, and this would be a pyridinium chloride, would be what you would call this. Now, if you're saying pyridinium chloride, where have I heard that before? Pyridinium chlorochromate has the pyridinium chloride part. The second C stands for CrO3. So pyridinium chlorochromate, or PCC, that we use to oxidize primary alcohols to aldehydes could very easily be used, or is the same pyridinium ion. So a lot of times what you'll see in this reaction is the addition of the pyridine to basically absorb the HCl to keep it from reacting further. Now, in this case, we have no choice. We have to use pyridine in this reaction simply because if I form HCl in this reaction, that HCl will react with any amine that's left over that hasn't reacted yet. And once I convert that amine to an ammonium salt, it isn't a nucleophile anymore, so it can't react with the acid chloride. So we would use the pyridine in order to basically convert the HCl into the pyridinium ion, again with the chloride as a counterion. So it's necessary to add pyridine, and pyridine's just a good base that doesn't really react. All it does is just absorb protons. It's kind of a proton sponge. So we would add the pyridine to make this amide reaction go. And the mechanism for this would be exactly the same as before. I'll go ahead and write it out just so you can get some practice. I've had all the practice I need. We're going to, again, the chloride in the acid chloride is removing electron density, making that carbon more delta positive so that a neutral nucleophile will add. Now, in this case, nitrogen is a better nucleophile than oxygen is. Remember, CNOF. Horizontally, basicity increases, but also horizontally from right to left, nucleophilicity also increases. So nitrogen is a better nucleophile than oxygen. So it didn't need the help, but it's getting it from the chloride. So the nitrogen comes in, adds to the carbonyl. We end up with our O- with our now NH2 with the R, a positive charge here. The O- you can say, okay, let's just deprotonate that with the O- so that we form this. So that we form that compound. Now remember that the difference here between this being what we called before a hemiaminal as the chloride, so it's a new species. And you can kind of think of this, our pyridine molecule acting as a base is going to come in and grab the hydrogen, pair of electrons moves, chloride leaves, so that now I end up forming the carbonyl along with the amide and the pyridinium chloride. So again, if I don't have a base in there to remove that nitrogen, it'll go back in the process, it'll go back in the system, it'll protonate the amine, and then any unreacted amine at that point becomes ammonium, which is not a nucleophile because it doesn't have the free electrons now to be able to react with the carbonyl. So that would be our mechanism for forming an amide from an acid chloride. So we can take an acid chloride and we can convert it to an anhydride, The best way to do that is using a carboxylate salt here. Using a carboxylate, that's the best way to do this. Then if we want to form an ester, react the acid chloride with an alcohol in the presence of pyridine to remove the H+. And if we want to then form the amide, react the acid chloride with the amine to go ahead and make the amide, again in the presence of our pyridine as our base. Okay, what else can we do with acid chlorides? We're kind of talking about the reactions of acid chlorides here. We can react them with lithium cuprates to form ketones. This is a review reaction that we talked about earlier, but we'll go back and remind you of it. Acid chloride plus lithium cuprate. Where'd the lithium cuprate come from? 2 equivalents of bromide plus lithium and copper iodide or copper chloride. So we make the lithium cuprate. What we talked about earlier is the fact that this lithium cuprate is less reactive than either the Grignard, there's parentheses here, either the Grignard or the organolithium compound. It's less reactive than that. We'll talk about that in a minute, what would happen with that reaction. So therefore only one of these is going to add, and I'm going to end up forming the ketone. So in this case, only one equivalent adds. And that's because a lithium cuprate is less reactive than a Grignard or an organolithium compound. Now, just to remind you that when we took an acid chloride and we reacted it with the Grignard, we needed to have 2 equivalents of the Grignard. We need to have 2 equivalents in that reaction, because what would happen is the Grignard comes in and attacks the carbonyl. And forms that species. Again, if an O- can bring the pair of electrons down and there's a leaving group, it will. And so what it ends up doing is it ends up forming the ketone. But the problem here is the timing of the reaction would be such that the minute you form some ketone and there is some organolithium or Grignard or organolithium compound left over, or that hasn't reacted, that would come in and react with the carbonyl. And what we end up doing is we end up adding 2 equivalents of the Grignard or the organolithium compound to an acid chloride. So we would get a whole mixture of products if we just use 1 equivalent, because of the sort of, as the reaction goes, the minute I form a ketone, if there's any Grignard there, it's going to react. So what we do is we just say, you know what, let's just use 2 equivalents and let's just go ahead and make the, and add both. In this case, the reaction's over, there's no more leaving groups. So then we would add RH plus H2O to that, and we would end up forming the tertiary alcohol. The tertiary alcohol, where 2 of the groups came from the Grignard. So that's the difference between a cuprate, which is less reactive only adds 1. The lithium cuprate, which is less reactive, only adds 1 alkyl group and makes the ketone, whereas the Grignard or organolithium compound is more reactive, and it's going to go ahead and add 2 to make the final tertiary alcohol. And so that's kind of a review reaction that we've done in the past. Okay, so here's our reactions of carboxylic acid chlorides. So if you want to make an anhydride, the best thing to do is to react that acid chloride with a carboxylate. The term mixed anhydride means that if I wanted to have an acid chloride with a methyl group on one side and I wanted to have an ethyl group on the other, I could add the different carboxylate salt with maybe an ethyl group here, so I could form a mixed anhydride. Now, typically we don't use those. We typically have the R groups being the same. So we would just go ahead and react our acid chloride again with carboxylate's the best way to do it. If we want to convert the acid chloride to the ester, just use an alcohol along with pyridine. If you want to make a ketone, we're going to use a cuprate. If you react it with a carboxylic acid, if you react it with a Grignard, which isn't here, but I'm going to go ahead and add. If you go ahead and add that with 2 equivalents of Grignard, you're going to go ahead and make the tertiary alcohol with 2 of the alkyl groups being the same. If you would like to make an amide from an acid chloride, react it with an amine. I guess what they're missing here is the pyridine, but you would want the pyridine to go ahead and add there. What they're doing is they're saying, well, add 2 because then you want extra amine to pull the proton off. I would just use pyridine. I would just use 1 equivalent with pyridine. And then finally, this other reaction we talked about earlier, and that is to react, if you want to take an acid chloride and you want to make an aldehyde out of it, what we need to do is we need to react it with a less reactive hydride source. Now, first of all, I'm going to add in a reaction here and say, what would happen if you reacted this with lithium aluminum hydride? What you would end up doing is reducing the acid chloride all the way down to the primary alcohol, like a carboxylic acid that we saw in the previous lecture. If you want, what you can do is you can take the acid chloride and you can reduce it to the aldehyde by using a less reactive, this is again a very reactive reducing reagent. Use a less reactive reducing reagent. What was that? The less reactive reducing reagent was lithium, aluminum, triterpenoxy hydride. That will only add 1 hydride and will produce the aldehyde. So that's an easier way of doing that reaction. You can also use, as it says, you can use hydrogen and palladium to reduce the acid chloride to the aldehyde. It can be done. It's not that big of a deal. So all of these different compounds can be made from a single acid chloride. And again, just to review here, where did the acid chloride come from? It came from the carboxylic acid and SOCl2 or PCl3 or PCl5. And while that mechanism is in the textbook, we're not going to basically go over it. We're going to save our mechanisms for things that are more important than that. So there are all of our different reactions that we can do with an acid chloride. Okay. And with that ends chapter 24. So now what we're going to do is we're going to talk about carboxylic acid derivatives and carboxylic acid derivatives. So I've done this probably multiple times, but I'm going to go ahead and do it again. Let's talk about what is a carboxylic acid derivative. Which ones are we going to talk about in chapter 25? Well, we've already talked about a couple of them in the previous chapter, in this lecture, and in the previous lecture, but let's list out the carboxylic acid derivatives. Carboxylic acid chloride, carboxylic acid anhydride, ester, and amide. Okay, so these are our carboxylic acid derivatives. There is another one that doesn't have that form, and that is the nitrile. So we have a nitrile, an amide, an ester, carboxylic acid anhydride, and our acid chloride. Now, we just looked at reactions of acid chlorides and formation of acid chlorides. We're going to look a little bit more at anhydrides, esters, amides, and nitriles in this chapter, making them as well as their reactions. I don't know why they put acid chlorides in chapter 24. I would have moved it to chapter 25, but I think because chapter 25 is already long enough. Okay, these are all carboxylic acid derivatives. What does it mean? What does the term derivative mean? The term derivative means that when you react each one of these compounds in a hydrolysis reaction, you form the carboxylic acid. That's what a carboxylic acid derivative is, and that's what a carboxylic acid derivative does. So when you hydrolyze a carboxylic acid derivative, you end up making the carboxylic acid. And that's true for all of these, including the nitrile. Now, we'll talk about the mechanisms for these. You can do hydrolysis under acidic conditions with H plus H2O. You can do them under basic conditions using hydroxide, H2O. Either set of conditions, base hydrolysis or acidic hydrolysis. Hydrolysis, lysis, cleave, like you learn in biology, hydro, water. So all of these are cleavage of water, and the molecules themselves are actually going to be cleaved as well to form carboxylic acid. So that is what a carboxylic acid derivative is. Anything that undergoes hydrolysis to form a carboxylic acid. Now, also what I want to do is go back, and I've done this a couple of times, but I'm going to redo this as well. The idea of substitution versus addition. And I think I did it at the end of one of the lecture periods. I want to take a couple more minutes and talk about this. So basically, with the exception of the nitrile, the other carboxylic acid derivatives all have a Y group attached to the carbonyl. They have an alkyl group on one side, and they have a Y group on the other. Okay. With the exception of nitriles. Nitriles are kind of which one of these things doesn't look like the other. But a carboxylic acid derivative that has a Y group attached to the carbon. What's characteristic of all of these groups? The characteristic of all of those groups in the boxes are that they could, and I'm going to use the word could, be a leaving group. Now, some of these leaving groups are better than others. Some of them we haven't really used as a leaving group unless we protonate them. Or in the case of the nitrogen, remember that when we did when we did Hoffman elimination, we alkylated the nitrogen to make it a leaving group. And then in Cope, we added an oxygen to it to make it an amine oxide as a leaving group. So those are pretty harsh, but these other ones we can get to leave. We can protonate an OR group and make it leave as an alcohol. Chloride, we know, just leaves on its own, and we'll see that the anhydride also leaves on its own. So I'm not going to say these are great leaving groups. I'm going to say that they could be leaving groups. Now, what can't be leaving groups? Groups that never act as leaving groups, H and C. So in carboxylic acid derivatives, you have a Y group that can leave. Okay. And you might say, but wait, carboxylic acids with an OH group, where would they be on this chart? The carboxylic acid group would be right here with its OH group as a potential leaving group. Now, I've ranked these in terms of leaving group ability, with the best leaving group at the top and the worst leaving group at the bottom. So chloride, better leaving group than anhydride, better than OR, better than NH. Okay. So basically what that means is, that means that acid chlorides are going to be the most reactive and amides are going to be the least reactive. We can also, because remember, in chemistry, reactivity stability is an inverse relationship. So you could say that the most reactive is the least stable, and the least reactive is the most stable. Again, I'm leaving nitriles out of this table. I'm only dealing with groups that look like this. I'm only looking at groups that have the carbonyl attached to a Y group, which could be a leaving group. Okay. So what am I going to do in this chapter? What have I already done with acid chlorides? What I did was I added a nucleophile to them. And let's just say for the sake of argument that I might add a nucleophile with a negative charge. What's going to happen? The nucleophile is going to come in, add to the carbonyl, pair of electrons goes up. So now I have my Y group, and I have my nucleophile that I just added. Now, there's two pathways that this reaction can go. The pair of electrons on the O- is going to come back down. It's going to try. What happens if the Y and the nucleophile, are not leaving groups? Well, that was the case when we had aldehydes and ketones. What happened? Nothing. The O- tried to bring the pair of electrons down, and neither group could leave. So it just kind of hung out and waited for the H plus to come in and protonate the O- to form the final product. Think Grignards. Think reduction with H- of aldehydes and ketones. So that was a primary pathway that happened with our aldehydes and our ketones. And that's basically what's called addition. All I did was add a group to the carbonyl, so it's actually carbonyl, or what's called acyl addition. But what happens if Y or the nucleophile could be a leaving group? So Y or nucleophile can leave. They are potential leaving groups. What happens then? Well, then the O- can bring its pair of electrons down, and something's going to leave. What's going to leave? Well, that's going to depend on what's the better leaving group. If the nucleophile is the better leaving group, what happens? We go right back to the beginning. Equilibrium. Okay. Well, where did we see equilibrium reactions? We've seen equilibrium reactions with hydrates, acetals, ketals, primarily because the Y group ain't leaving, because it's an alkyl or a hydrogen in the case of the aldehydes. What did we just see with the acid chloride, though? We saw that if the Y group is a better leaving group, then what happens? Then the Y group leaves. And what do I end up doing? Reforming the carbonyl, and now I've added the nucleophile. That is going to be what is called acyl substitution. So now in this case, I've substituted my nucleophile for my Y group. Let's just take a quick trip down memory lane here. All of these reactions are substitutions. I've substituted each one of those groups for the H. Some fit that mechanism. Some do fit the mechanism, they're just not as clear. So the difference between addition and substitution depends on, is the Y group a leaving group? Is the nucleophile potentially a leaving group? Which one's a better leaving group, the nucleophile or the Y group? Am I stuck at this position because I'm in an equilibrium? Am I stuck at this position because I'm in an equilibrium, because the nucleophile is better than the Y group? Can I move forward because Y is a better leaving group than the nitrogen? So that's kind of an overview of what Chapter 25, and to some extent what Chapter 24 was about, and to some extent the aldehydes and ketones chapter. So basically we've been doing this for the last 3 or 4 chapters. But that's our overall goal. And that's the difference between addition and substitution. Okay? All right, so here's that chart again. And what it shows us is that depending on the Y group, when I order them like this with the best leaving group at the top, what I can do is I can convert acid chlorides into all of the subsequent derivatives. Why? Because chloride's got the best leaving group. And so this is just another version of that chart. How do you make an anhydride? React the acid chloride with carboxylic acid, although we would prefer using an O- here. How do you convert an acid chloride to an ester? Use an alcohol with pyridine. How do you convert it to an amide? Use the amine. And I would use pyridine there as well. When you react the acid chloride with water, what do you get? You get the carboxylic acid. So as we go through these reactions, just keep in mind that chloride, most reactive, can be converted to an anhydride. The anhydride can be converted to an ester or an amide. you can't go up. You can't take an ester and make an anhydride out of it. You can't take an ester and make a carboxylic acid out of it. You can only go down. So then you could take an anhydride and make an amide. Esters can be made into amides. They all can be converted to a carboxylic acid by hydrolysis, either base or acid hydrolysis. Okay? So that's our overall goal here for chapter 25. And as I said, we've been doing this. So we're going to kind of take these. I've reordered some of these, but I'm trying to keep to what Top Hat has been doing. And so let's look at kind of the first reaction, which will be the last reaction that we do for this lecture video. And that's what's called transesterification. So let's say that I had a methyl ester, and I wanted to convert that to putting something like a ethyl group on there. This would be an example of transesterification. In other words, I'm going to change one ester into another. Now, let me review here for kind of quickly. Remember that in Fischer esterification, what we did was take a carboxylic acid and react it with an alcohol to make our ester. Now, an ester has an alcohol part, and it also has the part that came from the carboxylic acid. So when we look at carboxylic acid, when we look at esters, we're going to view esters as having part that came from the carboxylic acid and part that came from the alcohol. So what I'm basically doing in this transesterification is I'm replacing one alcohol part with another alcohol part. So all I'm going to do is this. I'm just going to say, okay, let's react that with ethanol. I'm going to need acid as my catalyst, and I'm going to need excess carboxylic acid. I'm going to need excess alcohol to make this reaction go. Okay. So what would happen here? What's going to happen is I'm going to protonate the carbonyl first. Then my ethanol, my other alcohol, is going to go ahead and add to that carbonyl. Oh, there's no plus charge there. Remember, I add the entire alcohol part, so there. I form that. Then I'm going to lose my H plus to regenerate my catalyst. Okay. There's nothing really new here. Now, what's going to happen? Well, I can add H plus to either of these OR groups. You might say, why not the OH? Try it. If you add an H plus to the OH, the water will leave and you're stuck. The water will have to come back in and add, because you can't form a double bond to either of those two oxygens. So the H plus is either going to protonate the OCH3 or the OCH2CH3. Now, if it protonates the OCH2CH3, you're going backwards. If, on the other hand, it protonates the OCH3, we can go forwards. So now the methanol can leave. And for time, I'm going to shorten this mechanism up and use the alternative one that I showed you in the last video, where I can bring this pair of electrons down and have the water leave, so I can lose H plus and lose the methanol, and you lose the methanol molecule to make the final carbonyl. So what I ended up doing was I ended up replacing the OCH3 for the OCH3. Now notice all of these are equilibrium steps. What's going to push this equilibrium overall? Let me just rewrite that equilibrium so that I can... How am I going to replace the OCH3 with an OCH2CH3? Well, in this equilibrium, what I'm going to do is I can go ahead and I can force the equilibrium to the right by going and using Le Chatelier's principle. So what I can say is I can say, you know what, if we use excess ethanol, then that's going to push the equilibrium to form the transesterified product versus having the methoxy group still there. So we just use Le Chatelier's principle and react the ester with an excess of the alcohol we'd like to transesterify with in the H+. And so what we end up doing is we end up pushing that equilibrium to the right. Now, in the mechanism, what that means is that even if the H+ comes in here and protonates the ethoxy group, eventually the methoxy group is going to leave just by random chance, and when it does, it's going to be replaced with the ethoxy simply because there's more ethoxy there. So this is an example of transesterification and the mechanism, and again, the way we push it is we use excess of the alcohol to replace one. In the next lecture, I will start with showing you a practical example of transesterification that is very useful in forming what is called biodiesel fuel. But we'll leave that for the next lecture. Okay.